Hello everyone, and welcome to another Absolute Minimum. Unlike all my previous videos up to this point, this one is actually not going to be about a text editor, and instead it's going to be about a library called Numba, which, as the tagline reads here, makes Python code fast. Numba is a just-in-time compiler, which means that it can take your existing Python code, try to figure out what types exist inside it, and then generate fast machine code from it. Looking through their website, you can see a number of examples in the main page, and all of them show that you can keep your Python code looking very much like Python code, and then add a decorator that just says, do just-in-time compilation. This is able to create code that's very similar to the speeds that you can get with C or Fortran or C++, but without having to write code in any of those languages, or without having to ship compile code, or expecting the user to have some sort of a compiler installed. Their website also demonstrates that Numba works well with Numpy arrays, which makes it really suitable for scientific computing. And finally, that it makes it really simple for you to parallelize your code and use multiple threads. It also does a very good job at doing SIMD vectorization to get the most out of your CPU, and if you want to go to the next level, you can even run Numba code on GPU. While my video today is going to cover most of the basics, things that I think that you'll need 90% of the time, there are other videos and other tutorials out there that I recommend you look at. And one of the ones that I really like is from one of the core developers of Numba called Accelerating Scientific Workloads with Numba. This talk is particularly good because it shows examples of other people using Numba for open source projects, things that you may have already used. For example, if you've ever used Data Shader for visualization, you've already used code written with Numba. Okay, so without further ado, let's dive straight in and see what Numba is all about. One of the other things that's going to be different about this video is that instead of working in an editor, I'm going to be working in a Jupyter notebook, which is an environment that I feel is very useful for experimentation and for slowly discovering a problem or a new library. So we'll go ahead and make a new Python 3 notebook. And usually the first thing I do for exploration related tasks is if I need to plot things or use NumPy, I do the lazy thing and just run pylab inline. This is a nice Jupyter magic that will import a lot of really useful functions, as we'll see in a second. So let's first go through the example that's given on the Numba website. Now, normally when you're trying to accelerate a function using Numba, you can use a decorator. But since a decorator is just a function that takes a function as an argument and then spits out a function, I'm going to remove that here so that I can retain the main function and run this. And then let's get a baseline for how long this function needs to actually run. Now, the number of samples here, let's use a high value like 1000. Okay, 1000 is not high enough. Let's use 10,000. Okay, so this is starting to get into code that takes a reasonable amount of time, 7.41 milliseconds. Now let's make a JITted version of this. And to do that, we can define a new function and then run the timing again. Okay, what's going on? The whole premise of this video is that you can make your code really, really fast using Numba. And I go ahead and I run this function and it actually takes 100 times more roughly than the pure Python version. So what's going on? Well, because Numba is a just-in-time compiler, the first time you call the function, in this case, it's actually going to spend some time compiling the function. Now that you've run the function and the compilation has been done and all that code has been cached, you can run it a second time and presto. Now it only takes 189 microseconds as opposed to 7.41 milliseconds. So this is a good initial demonstration of what Numba can do, but at the same time, we can see a pitfall, which is that the first invocation of a function needs the compilation time, which means that there's going to be a delay. This is something that'll come up over and over again, and a lot of people get tripped up over. So I wanted to cover this. Okay. Now let's move forward. And one of the things that I wanted to do before getting into some serious optimization with Numba was show you all the various ways in which you can fail to do things right. I think it's very important to see this with Numba because it is kind of easy to fail in many situations. And if you don't know what's screwing you over, you could spend a lot of time just trying to figure out what's going on and, waste a lot of time, which is in many ways antithetical to what Numba is trying to be. So let's import pretty much everything that I think we'll need from Numba. And in a moment, I'll go through what each of these are. So I'm going to put together kind of a really dumb function so we can play around with it. All this function is going to do is it's going to take in a list of numbers and create a new list that contains a 2 if the original number was even and contains a 1 if the original number was odd. And let's give this function a test array to use. You may have noticed I'm intentionally doing something weird inside this function, where when item is even, I'm appending the number 2, but when item is odd, I'm appending the string 1. We'll see in a second why I'm doing this. If we go ahead and run this function, it takes about 17.5 milliseconds to run in Python. Now let's make a JITted version of it. So when we run this function, we get this angry red box yelling at us. It's a warning, it's not an error. So the cell runs and completes just fine. Let's ignore the error for now. Looks like it took 337 milliseconds to run, but that's okay. We know that the first run is supposed to do the compilation. So let's run this cell again. And what gives? Again, a function that's been JITted using Numba is slow. Well, we should look at that warning again. What this warning is telling us is that there's something wrong with this else statement where we're appending a string. Essentially what's going on is that Numba thinks that this output list is supposed to be a list of int64s, which makes sense because in the if statement, we're appending a 2 to it. And Numba is automatically assuming that that 2 represents int64 because it doesn't know any better. And then when it gets to the else clause, it sees that the string is being appended and that doesn't work. It can't generate efficient code for this because we're mixing types and that's not something that Numba is able to do. But it is something that Python is able to do just fine. Now, in an effort to make Numba user-friendly, the main JIT decorator is designed to not fail in these situations, and instead it falls back to something called object mode. Object mode is not your friend. All object mode is essentially doing is generating code that looks very similar to Python, where it's trying to figure out what the types are or trying to be flexible in types, and this actually ends up hurting you. As we've seen before, when we run this function a second time, it actually takes longer than the pure Python implementation because all we've done is created a function that is as slow as the Python implementation, and then on top of that has Numba's overheads on it. We don't want this. Now, the simple fix here is, of course, to change the string so that we're no longer appending a string. But before we do that fix, I want to go over what I think that you should be doing in your Numba workflows, which is to never use the JIT decorator by itself, or just don't use the JIT decorator at all. Either use the njit decorator or use an option called noPython equals true. Now, if I run this function, I don't get a warning. I get an error. It's not going to let me proceed. And that's good for development of really high performance code, because if at some point, here I inserted an obvious bug, but sometimes these bugs are not obvious, especially if you're really used to working in Python. It's easy for you to mix types or write code that wouldn't necessarily generate really efficient machine code. So making sure that you always run in noPython mode makes it so that you always get an error as opposed to a warning, and then you can't proceed and you have to go ahead and fix that error. I find that the Numba error messages are usually good at telling you where to go. They're not always necessarily good at telling you what's wrong, so it can get a little bit frustrating. But if you write your codes with small functions that are very specialized, this problem happens less and less. So essentially what the noPython mode is telling Numba is that you can't turn to the Python interpreter for any help whatsoever. And this essentially ends up being the most pure mode of Numba. The Numba developers have recognized this should be the correct way to do things. So they already give you a decorator called njit, which automatically sets noPython equals to true. So if we just take this out and change the decorator to njit, run the code now, we get an error. So let's go ahead and fix our code. When I originally defined this function, I didn't say that it was going to be appending a string 1. I said it was going to be appending a 1. So this code is busted. Let's fix it. Running the original function in pure Python mode, it doesn't really change anything. It takes the same amount of time to run. But now if we JIT it, run it once, we get a wall time that's way higher, but we know that's fine. There's compilation happening. There's also another error that we get, and this is going to mess us up in like just a few minutes. This error is telling us that we are passing a Python list to this JITted function, and Numba has to do extra work to figure out what's going on in this list. And for that, it has to use reflection. But that's something that the Numba developers have realized is not very good to have as a supported feature. So they're going to be deprecating it soon. So for the purposes of demonstration for now, it's fine, but I'm going to move away from using a Python list in a second in this tutorial, and you should also never use these. Anyways, if we go ahead and run this again, okay, what gives? It is still taking, now it's taking even longer than it was taking before. And that's because of the reflection problem. Even in this noPython mode, Numba is having to rely on reflection to figure out if the type of the input array is correct while it's running. So this is even worse than before. The moral of this little story is that you should try to avoid using Python lists with Numba whenever you can. And that's fine because in most cases, everything that you need to do will happen fine with numpy arrays. If you want to learn more about this, I recommend that you read this list topic in the Numba documentation. I'll link it down in the description. But they explain all of this, and they explain that this behavior is going away, and they have introduced a typed list, which is an experimental feature right now, but that will replace passing Python lists, and then this problem wouldn't happen. So how do we fix this? Like I said, it's better to be using NumPy arrays anyway, so let's redefine test array not as a normal list, but as a NumPy array. As a consequence, this actually slows down the pure Python function. I assume this has something to do with iterating through NumPy arrays in Python, something that I'm not really aware of and am not qualified to comment on. It just happens. However, now if we run this function, it is running at about 5 milliseconds, compared to the 20 milliseconds that the pure Python implementation was with a normal Python list. So at this point, I want to take a small detour to discuss another feature of Numba, which is actually really nice, but we're not going to spend too much time talking about it, because once you know the rest of Numba, you can sort of just include it wherever you need to. And that is the Vectorized decorator. What Vectorized does is it allows us to rewrite this function as a scalar computation. So we have rewritten the main part of the computation is in this original function, but instead of having the function operating on a list, we're having it operate on a single element of that list. However, the Vectorized decorator has created a function that can accept both a normal number and our test array. If we go ahead and time this is interesting, isn't it? Calling this vectorized implementation is taking less than a millisecond, whereas what appeared to be the same function is taking 4.83 milliseconds. This actually has to do with the structure of the original function, where we are defining an empty list and then appending to it. So there's no way for the compiler to know what the size of this list was supposed to be, which means that it can't really do any pre-allocations and we lose a bunch of time. We can fix that by rewriting this function. And now it takes about the same amount of time that the vectorize function takes. So ultimately, whether or not you use vectorize comes down to how you want to write your computations and if you want to explicitly or implicitly pass arrays to them. Vectorize is really nice for simple computations, and the fact that it works both on scalars and arrays, whereas the fixed function is only going to work on arrays, is a big boon. So now that we've seen a number of different ways that we can fail to write good code in Numba, let's look at just writing performant code in Numba and taking a simulation, making it really, really fast. The motivating example for the rest of the video is going to be a spring mass damper system. Normal spring mass damper systems, or harmonic oscillators, are represented as a second order system of linear differential equations, ordinary differential equations. And they have this really nice property where the initial condition does not change the overall behavior of the system. I've prepared this example, which is a similar dynamical system, but whereas a normal spring mass damper system contains what's called wet friction, which is friction that is a function of velocity, I've defined a friction term that is both wet friction and dry friction, where dry friction is a constant value as opposed to a value that depends on the velocity itself. You don't really need to understand what these functions are doing, other than the fact that they're simulating this funky spring mass damper system that I've defined for 10 seconds with a very fine time resolution of 1/10 of a millisecond, given some initial position of the spring mass system. So if I simply call this function with some initial condition and time it, it takes about 291 milliseconds. If I were to plot it for different initial conditions, these plots don't seem to converge at the same location. This is very different from a standard spring mass system. In addition to this system can no longer be modeled with ordinary differential equations, which means that it can't be solved using standard techniques that we use to solve the spring mass damper system, which means that if I want to study its behavior for different initial conditions, probably my only option is to do simulation. Now, imagine for a second that I'm a PhD student and my advisor comes and it says, hey, you need to simulate this system for initial conditions going from 0 to 10,000 at 0.1 increments, and then do some statistics on it. So me, as a grad student, I fire up my calculator. 10,000 divided by 0.1 times 0.3, that's 30,000 seconds, divided by 3,600, that is 8.3 hours of my life, where I will just start the simulation and then come in tomorrow and look at it and hope everything worked out, and then just hope that my professor doesn't come back and give me a different range to run again. This is a long time, and this is not ultimately a lot of computation. The reason it's so slow is because we've written something in pure Python, and then we're trying to run it over and over again with lots of loops. Numba exists exactly for this. So let's go ahead and JIT this. Some things to note about how this function is written. I have made sure that arrays for time as well as the position that we're going to be tracking are pre-allocated in the beginning. In addition to that, when you're writing Numba code, sometimes you have to give up some normal Python conventions. So here, instead of using enumerate, I'm just using range, passing it the length of times, and then holding on to the counter variable so that I can use it to both retrieve the time as well as set the position. In normal Python code, writing this is very un-Pythonic. But in Numba, you're going to see yourself do this again and again because maybe things like zip don't work correctly. Maybe they do now. Last time I used it, they didn't, etc. So every once in a while, you'll run into some issues where some Python feature is not supported and you'll have to write your code. I like to say it kind of starts to look like if C looked like Python. I think that's an okay compromise for the speed boost that you're about to see. Okay, so now that we've JITted these functions, let's go ahead and run them. First compilation takes 250 milliseconds. Second run, it takes 1.63 milliseconds. So as a grad student, I go ahead and pull out my handy dandy calculator again. Look at that. I've taken a computation that was going to take 8.3 hours and converted it to 2.71 minutes. That's amazing. Well, let's make sure the data looks correct. So if you recover plots that look just like this, then it's probably doing the job correctly. And the plots do look like that. Life is great, right? Well, maybe life is great, but maybe I need to keep simulating these systems with slight perturbations. If I need to do that, then 2.71 minutes actually might end up being quite a drag. Now, my computer happens to have 8 cores, and many modern computers are going to have a lot of different cores available to them. So I'm this grad student. It's going to take 2.71 minutes. I think that I can do better because my computer has 8 cores. I go ahead and from concurrent futures, grab me a thread pool executor and then say with thread pool executor, I have 8 cores available. Take my function. I give it my list. I'm actually not going to run it for up to 10,000. I'm only going to run it up to 1,000. And that's a RAM consideration. Just as an FYI, we'll just cut everything down by a factor of 10. So I go ahead and run that with a time magic at the top of the cell. And if I look at htop, the activity in my threads hasn't really gone up. Now, originally this operation was supposed to take 163 seconds. We cut the input size down by 10, so it should be taking about 16 seconds. We're not really seeing much of an improvement. Well, that actually makes sense because Numba by default does not release the global interpreter lock. So using threads inside Python can't really give us any benefit here because each thread is still wanting to get the global interpreter lock before they can do anything. One of the nice things about Numba is that it's very easy to instruct a function to release the GIL. This function does not need to access the Python interpreter while it's running. In fact, we've made sure of that. So we can additionally tell it to release the GIL. And we can do that for the function that it's calling as well. Now, if we come back here and run this whole mess again, under htop, you'll see all of my CPUs saturate for a second, and the whole thing now runs in 2.77 seconds. So we have now taken something that was going to take 8.3 hours and is now taking 2.77 seconds times 10. That's about 1,000 times speed up. So yeah, that's my mic drop moment. If you have heard of Numba, if you're on the fence, if you're curious, if you have CPU intensive workloads, if you're doing any kind of scientific computing or computer vision or AI or anything where you maybe find yourself turning to C or C++ or Python, give Numba a shot because as I've shown tonight, it can give you about 1,000x increase with basically no additional work. And that's amazing. Now, before I finish this video, there are 2 additional things that I want to talk about. One is that you don't actually have to use the thread pool executor directly. Numba actually makes it fairly easy for you to parallelize your code, but we do have to define a wrapper function for that. Okay, before we run this wrapper function, a few things to note about it. In the ngit decorator, we set a keyword parallel equals to true. In addition to that, we import something from Numba called prange. It just stands for parallel range. It just instructs Numba, try to see if this function can be parallelized, and if yes, schedule the computation inside in different threads. In this case, this is an embarrassingly parallel problem, as we've shown before with the thread pool executor. So let's see what happens if we run these simulations again. It takes about 2.05 seconds. That's a little bit less than before. In some cases, that advantage of using native parallelization from Numba would be very helpful. In other cases, it wouldn't be. It just comes down to the particular problem that you're trying to solve. So I think up to this point in this video, I have covered 90% of what you'd need to do great things with Numba yourself. For the remaining 10%, you can discover some deeper topics in the Numba documentation. There's some really cool things like defining convolutions like you do in neural nets. There is an experimental feature that lets you define classes, but this is still experimental. You can define Numba functions to be called from C and C++, which can have some really cool uses. You can use something called fast math, which is approximate mathematics, and there's a number of other things. All of these links will be in the description. I'm just going to pop off real quick what other things I think would be useful for people to go and study on their own. It's definitely a good idea to look at what features of both Python and NumPy are supported directly by Numba, as well as some important differences from writing normal Python code and writing Numba code. You can also define types in your decorator for the function definition, which allows the function to be compiled when it is first loaded into memory as opposed to when it is first called. It is possible to debug Numba code using GDB, and you can read more about that in this article. And then if you're writing a library that you're going to distribute using PyPI or some other method, then ahead of time compilation might be a good thing to have. And then one of the standout features of Numba that I haven't covered in this video but might cover in a future video is that it makes it really easy for you to write kernels for CUDA or supported AMD GPUs so that you can massively parallelize your computations on a GPU. Okay, and that's all I got for this absolute minimum about Numba. This was my first Python related video. Please let me know in the comments what you thought about it. Give it a like if it taught you something new. If you like my content or how I do things, please subscribe. I'll be making more videos about programming and text editors and all sorts of things. Thank you very much for watching. Bye.